Okay, let's start with some recap questions. So chromatography is going to spread over a few lectures. After finishing principles, we're going to do HPLC and GC. So it's good to keep reviewing the concept of chromatography up until the first quiz, which will be October 3rd, I believe. So yeah, what I want to say, you are a very quiet group compared to previous years. Which is nothing wrong about that. But I just want to remind you that asking questions are also part of participation. Please interrupt me. I feel that I'm going faster in my lectures than last year because last year I used to get a lot of questions. So don't have me talk and talk at you. Try to ask questions. And really, this is a topic that is, I know you heard of it before, but it's not easy. So the more you ask questions, it will help others in the class. I bet if you ask questions, probably 5, 6 others will have the same question. So it would be good to stop and talk about a certain concept rather than me continuously feeding you new concepts. So please be encouraged. No question is a bad question or a stupid question. All questions are valid questions. And I don't mind at all getting questions. Okay. Let's have you talk a little bit. Recap from previous lecture. Define chromatography. I'm standing away from Alex this time. She already did it last time. Okay, define chromatography. Axel. It's a separation technique used in food analysis. We use it for many different applications. We will be talking about many applications throughout the semester. You'll see, like when we go into the carbohydrate chapter, there will be a lot of chromatography. When we go into the fat characterization, protein characterization, we will contaminants of concerns, we're going to bring back concepts of chromatography and look at applications. So now what we're doing is learning the principle, and throughout the semester we'll see applications. Okay? So many applications. Separation of constituents. This is the definition of chromatography. We're separating constituents to identify them. Well, first detect their presence, identify what they are, and quantitate. Oftentimes quantitate. Sometimes we just fractionate. That means use it as a way to concentrate and produce a certain fraction in a considerable amount. So what's the difference between stationary phase and mobile phase, and what is its function? Don't look at your notes. Just try to remember without looking at the notes. What is a stationary phase and a mobile phase in chromatography? From literal translation. Don't be shy. Go ahead, Alex.
So the stationary phase is what stays in a column and it tracks whatever compound is in your solution. And mobile phase is what runs through the column and is what carries along your thing and separates it out.
Awesome. So stationary phase is the phase that if you're using a column, or if it's a planar, if you have a plate, either paper chromatography or thin layer chromatography or a column chromatography. So the stationary phase is the phase that doesn't move and interacts with your constituents. So key is interaction. Your constituents is going to interact with the stationary phase, and the mobile phase is going to carry it along, move it along. And the speed of movement, it depends on how strong your compound is interacting with the stationary phase. The more it likes the stationary phase, the slower it's going to move with your mobile phase. Okay? So the less it likes it, it will like the mobile phase more. It will move faster with the mobile phase. Okay. What are the 3 types of chromatography? Nico.
Gas chromatography, liquid chromatography, and superfluid or supercritical fluid chromatography.
Yes, thank you. When I ask for types, This would be like a very common questions in a quiz or an exam. What type of chromatography would you use? What mode of separation would you use? Okay, so what type? First you would say HPLC. Mode of separation, reverse phase chromatography. Okay, so yes, so types of chromatography: gas chromatography, supercritical, fluid chromatography, and liquid chromatography. What is the form of mobile phase in GC, and what is the form of the stationary phase? Go ahead, Jacob. Yeah, helium is a gas. Yeah, okay. And the stationary phase? Yes, mostly GC is a liquid immobilized on solid. It used to be called gas chromatography, gas-liquid chromatography, because of the stationary phase being liquid. Okay. Same question for partition chromatography. What would be your mobile phase and what would be your stationary phase in partition chromatography? Now, Fan?
Yes, closed down liquid in partition chromatography, and for absorption chromatography, your stationary is solid, and your mobile phase may be gas.
It's liquid. Yeah, here we're talking about liquid chromatography. Okay. Yeah, but you're right. Partition, you're partitioning between two liquids. So stationary is a liquid and mobile is a liquid. Adsorption, mobile phase is a liquid. However, the stationary phase is a solid. Okay. What is a partition coefficient? What is a partition coefficient in partition chromatography? It's the concentration of a solute in the stationary phase over the concentration of a solute in the mobile phase. So it's basically your solute is partitioning between the two phases, and at equilibrium there will be a certain concentration in the stationary phase and certain concentration in the mobile phase. That is the partition coefficient. Okay, and we stopped at this slide. We didn't ask that question last time. I'm just checking here really quick if I'm recording. Yes, I'm recording. Thought I didn't hit the record button. Okay. So in reversed phase paper chromatography, the most polar travels the most. The least polar travels the most. RF value of the polar compound will be higher than the less polar one. RF compound is the ratio of the distance moved by the constituent over the distance moved by the solvent. Okay. Go ahead, Nick, right? Mm-hmm. The least polar travels the most. Say, you want to say something?
Oh, because in normal, right, it's the stationary phase is polar, and this is just split.
Yes, but if the stationary phase is non-polar, your least polar, that means the most non-polar, what will they do? They will not want to travel. They want to stay more with the stationary phase. Yes, Ali? It's A and C. Let me think of C a little bit. So value of the polar compound will be higher than the, yes, A and C. Correct. All right. Moving on to thin layer chromatography, which is another planar chromatography. So the planar chromatography is paper and thin layer chromatography, and the column, and there's the column chromatography that we'll move on and talk about later. Thin layer chromatography, or TLC. TLC, what does it stand for other than thin layer chromatography?
Tender love and care.
Tender love and care. Well, I'll tell you a funny story. I always tell the same story. So when my daughter was like 3 or 4, it's always my daughter's stories. She hates it. But When she was 3 or 4, she was at daycare, and I was coming to pick her up right after analysis class teaching TLC. And then I went in and she was crying and sitting in the teacher's lap, and I go, "What happened? Your daughter needed TLC." I was like, "What? Thin layer chromatography? Why would my daughter need thin layer chromatography?" And she goes, "No, tender love and care." What is thin layer chromatography? So yeah, that was my first introduction to tender love and care. So there we go. Similar principle as paper chromatography. So here is, you can buy them already made. They come in different sizes. Or when I was a student many, many years ago, we actually used to pour them ourselves, and I'll show you a slide later on. So it's basically the same principle where you would have a stationary phase. In this case is immobilized on a either aluminum or glass. You can use an inert surface, and you use silica most of the time, silica slurry, and then you spread it, and it's a thin layer of a stationary phase that will replace the paper, which is made of cellulose. It was developed to replace paper chromatography because you get better resolution. Again, resolution is the separation. Okay, so you get better separation because of its uniform particle size. So the silica slurry, when you spread it out and when you dry it, then you will have really very small and uniform particle size, which makes the separation better and faster. And here also better reproducibility. That means whenever you run it, you have similar results, more so compared to paper chromatography. Yeah, so this is the way we used to do it back when. So we used to get a square glass and clean it very well, dry it very well, and then prepare a slurry of silica, and then pour it and then spread it out using a tool similar to a ruler. And after we spread it out, we let it dry in the oven for a little bit, and once it dried out, then we can use it. Usually the thin layer, we make sure it's about 250 micrometer thickness, so it's a very thin layer of sorbent, and it's bound to inert support, so glass, plastic, aluminum foil. Often, like I said, it's silica, but silica is slightly acidic, alumina is slightly basic, or cellulose, which is neutral. Can be applied as adsorptive. You dry out the silica and it becomes adsorptive chromatography, mostly polar or normal phase. Or you can have a water, so you can keep it as a silica gel water, so that becomes normal phase. Or you can have, not in water, in an organic solvent, you have that layer over the silica and then it becomes reverse phase. Or you can take the some OH groups, if it's cellulose or other groups on silica, and then you can attach an ion or a charged molecule, and then it can be run as ion exchange. So since it's the same principle, so basically it will need a chamber where you would have your the plate after you spot your samples, and then you add your mobile phase, which is an organic solvent if it was, say, normal phase chromatography, and then let it develop, and then try to, if you want to see the spots, you use colorimetric development, so you can spray with anhydrine if it's amino acid. You can spray with sulfuric acid, which burns anything organic, so you would see burnt spots. Or iodine, or iodine vapor also will generate color. Or dichlorofluorescein, for example, like in this example here, where we're separating different fat components. And then measuring, if you can measure absorption, you can measure absorption or measure fluorescence. if you label your compounds, you can do by radioactive label, then you can do radioactivity measurement. So it's a qualitative technique usually used for screening. And then once you separate, if you want to quantify a certain component, you can scrape it off and then clean it using a cartridge. We call it, you elute the compound out of a cleaning cartridge. You let it run through a cartridge, and then you collect the liquid that comes out. So that means you're removing any silica residue or any stationary phase residue. And then you can take that solution and do another analytical technique to quantitate. Okay, any questions? Oh gosh, guys. Hopefully you'll get more talkative over time. I'm not intimidating, am I? Yes. No. I hope not. Okay, so that's planar. Column chromatography. We have two different types of column chromatography. We have the low pressure column chromatography, and we have the high pressure liquid column chromatography. The high pressure, you know it as HPLC, it's also known as high performance liquid chromatography. This we'll talk about in a separate set of lectures. But here I'm going to introduce the low pressure column liquid chromatography. So basically we call it column because you get a column and you fill it with your stationary phase. So they come in different sizes. So you have a really large column. Actually, they can be columns as big, reach out to the ceiling. They can be even bigger column on industrial scale. So I told you last time Agropore produced whey protein isolate using column chromatography. So they really have large columns. Or it could be smaller scale columns like that. So it really depends on your purpose. Why are you separating? Are you separating to just identify and quantitate? Then you might want to use a small column. If you, so that you only inject a small amount of sample. Or if you want to collect so that you have few grams of a fraction that you can do another analytical methods on or do a series of analysis on them, then maybe you want more media, more stationary phase, and you inject more sample and you collect more fraction each time. And also they differ in length. Sometimes the same diameter but longer. The longer the column, and I'll talk about that more when we talk about resolution, the longer the column and the more media in the column, you get better separation. Okay. If you're really looking for very good separation between compounds that are very similar in physicochemical characteristic, then you go with longer column. We'll talk more and give examples more later. So in a system with low pressure liquid chromatography, you have the column, you fill the column with your stationary phase. I want to say stationary phase filling of a column is kind of an art. Have you done that, Alex? Do you want to speak to that a little bit?
I guess.
Yeah, tell us how you fill your column.
So basically,
Listen to Alex, yeah.
I've only ever done wet packing, but you take your mobile phase and you stir in usually silica or whatever your stationary phase is, and then while it's like mixing and suspended in solution, which is hard because a lot of times it wants to settle down, so you have to keep it stirring, and then you basically pour the mixture into the column, and so your mobile phase runs out, and what you have left is your stationary phase, or yeah, your stationary phase that's packed in without any air bubbles, just like perfectly even.
Yeah.
And that's very concentrated.
Yeah, and then you regulate the pressure because there's for every media there's a certain pressure that you're able to apply, and then it helps with packing. The more pressure you have, the more packed your column is going to be, or the stationary phase. So it's really an art, and it requires lots of training to be able to do that, where you pack your stationary phase adequately so that there's no spaces, empty spaces or vacuum or bubbles, and it is consistent, so to allow for good resolution. So let's say you are trained and you packed your column and you have your stationary phase already there, ready. And then what you have attached to your column, which you use to pack your column, is your mobile phase. So sometimes you have one mobile phase. If you have one mobile phase, one concentration, and it doesn't change throughout your run, this is important and it will come a lot in quizzes and exams. So when your mobile phase does not change and you use the same concentration throughout the run until all of your solutes come out, we call that isocratic elution. Okay? Isocratic elution. Nothing is changing in the mobile phase. Nothing is changing in the flow rate or temperature. We will learn about flow rate and temperature later on and the impact on resolution. But everything is constant. That is called isocratic elution. So with isocratic elution, you will have only one solvent, one mobile phase. Ignore this for a minute. And then you will have your, it doesn't have to always be on a stirrer unless your mobile phase would like to separate, but oftentimes it is stable in solution. And then you have a peristaltic pump that will pump your solvent onto the column. There is usually an injection port in between. Somewhere here there will be an injection port where you inject your sample. We use oftentimes a needle to inject our sample, a syringe, to inject the sample, and then the sample will be carried with the mobile phase onto the column and goes through and start interacting with your stationary phase and separate based on the affinity of your compounds to the stationary phase. Those that like the stationary phase more will linger on it. Those that like it less will move faster through the column. So after the compounds get separated and they move down the column, and as they elute out of the column or leave the column, they get to a detector. Sometimes you have a UV detector, sometimes you have a refractive index detector, sometimes there is a photodiode array detector. So there will be different types of detectors. We'll talk about them in the HPLC lecture. So it goes through a detector, and if it's a UV detector, that means your compound absorbs UV light. So you are either measuring absorption or emission of light, and then you get a signal. As the peak comes out or as your compound comes out, you see peaks, and that is a signal of absorption. What is nice with low pressure chromatography and a large column is you can actually collect fractions. So after they go through the detector, you would have a tray. Usually it's a circular tray with tubes in there. You time it. Time it based on when each compound or fraction is going to come out. And then the tray starts moving and then fills in your fractions. And then it moves to fill another tube and so on. You can take each fraction and you either do more analysis, or if you're collecting certain type of protein to do certain type of analysis, you can freeze dry it and then run analysis on it. You can do other analysis as well. Let's say you don't want to do UV detection alone. You can have a valve that opens it and goes to another system that you have as an automated system. Let's say you're measuring a substrate for a particular enzyme. You will have your enzyme, your reagent. It reacts with the enzyme and reagent and gives you enzyme activity. You can either use that to determine, if you're separating enzymes, to determine the activity of the enzymes as they go out of the column. Or if you're separating substrates for an enzyme, you can use that to quantitate these substrates. So you can either just detect their presence or determine activity of certain compound or molecule coming out of the column. So let's talk about gradient mobile phase. A gradient mobile phase, and again this is very important, is you have more than one solvent. In this case, you program your mobile phase to change in concentration over time. So let's say it's a normal phase, or let's go with reversed phase, because you're going to be doing that in the lab. In reverse phase, you start with a polar stationary phase. Then what happens is your compounds are going to interact with your stationary phase, but now you want them to come out, and come out before time to go home, or before lunch, or something. So you do something we call increase the strength of your mobile phase. Increase its power so that it can pull these compounds out of the stationary phase. In order to increase its power, you go ahead and add organic solvent. So, and that is an example of only reverse phase. You don't always add organic solvent to increase the strength. It depends on the mode of separation. That is a very common mistake that students would make. How do you increase the strength of the mobile phase? Increase organic solvent. No, we don't increase organic solvent when your mode of separation is normal phase, for example. Okay? So you have to always remember, what is my stationary phase? What is my mobile phase? How can I make the mobile phase stronger to compete with the stationary phase? So if my stationary phase is nonpolar, to make my mobile phase stronger, I make it more nonpolar or less polar. Okay? But the opposite is true. If my stationary phase is polar, my mobile phase is nonpolar. In order for it to compete with the stationary phase, I make it more polar. I would add water. So it's the opposite. So increasing the strength of the mobile phase doesn't mean that you add water all the time, or add organic solvent, and then later when we talk about ion exchange, change the pH or add salt. It's not always in one direction. It really depends on what the type of stationary phase you have. So think about increasing the strength of the mobile phase. It means making it stronger than your stationary phase, more powerful for the compound to leave the column with the mobile phase, rather than staying on the stationary phase. Think of the justice example. Buy her something that is on the stationary phase in the store, so she can take with her and leave. Yes, Jacob. Oh, you can pack your material dry or wet. So you can, it's more often you pack it as a wet, like a slurry, mixed with a mobile phase or water or whatever it is. Or sometimes you just pack it as powder, but this is very rare. It's often packing the column as a slurry. Okay, so the gradient is changing the concentration over time during an elution or during a run. Okay? So the concentration of the mobile phase is not the same throughout the run from beginning to end. That means I am increasing the strength of my mobile phase over time. So sometimes I don't need to do that. My run is fast and I get good separation. I don't need to increase the strength of the mobile phase. Sometimes I'm separating compounds that are very different. Some are very polar, they're going to leave right away. Let's say if my column is nonpolar. And some are very, very hydrophobic. They don't like polar mobile phase, so I really need to increase the strength of the mobile phase. And again, this is an example. All right, questions? Yes, Alex. If you have two completely different mobile phases and then you're mixing them together, then yes, it's gradient. If you're doing one and then switching to the other, it's still gradient. If it's still considered gradient, although the word gradient means that you are slightly increasing the concentration, But even if you're moving abruptly from like salt to water, you change the concentration of your mobile phase, basically. Yeah, I know the word gradient means that it's gradually changing, but sometimes you just abruptly change altogether. Yeah. But even if you abruptly change, it takes it time to get the salt out. Yeah. I'm saying salt because I'm thinking of hydrophobic interaction chromatography, but yeah. Okay, so the other type that I'm going to talk about, so we talked about GC briefly, liquid chromatography column, planar and column briefly. I just want to introduce supercritical fluid before going into different modes of separation, going back and focusing more on liquid chromatography. So supercritical fluid, from its name, it's supercritical. You reach the mobile phase that you're using is above its supercritical pressure or temperature. So oftentimes in supercritical fluid chromatography, you use a mobile phase that is liquid carbon dioxide. So the liquid carbon dioxide is basically a compressed CO2. So when you pressurize CO2 and you are above a supercritical point of pressure point, then that CO2 becomes compressed gas in liquid form. So the compressed gas, the liquid CO2 has high diffusivity and low viscosity. This is a very good characteristic to have a quick run, quick analysis, as well as better separation. You get very sharp peaks, and we'll talk about peaks and sharp peaks later on. But I just want you to remember that with liquid CO2, it's really very low viscous and it moves very fast. And when it moves very fast, your compound can move in and out from stationary phase to mobile phase and reach equilibrium faster. So you get better separation and a short analytical time. So that is the main advantage of supercritical fluid chromatography. Sometimes if your compounds that you're trying to separate are a little bit more polar, liquid CO2 alone won't help them come out of the column. So you add a little bit of methanol, which is a polar organic solvent. So you will put that in there to help with separation and removal, elution of slightly polar compounds. So often it's used for nonpolar molecules and those molecules that are not volatile and thermally labile. Otherwise, instead of using GC requires that your compound is volatile and it doesn't degrade with heat. So when you can't use GC and you have nonpolar molecules, then you can use supercritical fluid chromatography. Stationary phase that is used is similar to the stationary phase used for HPLC, and we'll talk about that. Similar as to the equipment used for high-performance liquid chromatography, and we'll talk about that when we cover that part. And detectors are similar to those used for GC. Again, you'll learn about GC detectors later. So just remember that stationary phase and equipment are similar to HPLC. Detectors are similar to GC. That's what you need to remember for that supercritical liquid chromatography. Okay. So now that we introduced all types of chromatography, we're going to talk about mode of separation. Or in other words, the physicochemical principle of chromatography separation. The basis of separation, the physicochemical basis or principle of separation. We have several modes of separation that we use in liquid chromatography. This is only applies for liquid chromatography. It does not apply for gas chromatography. So we have the adsorption chromatography, where your solutes adsorb to the surface active groups of a stationary phase, and they adsorb via different molecular interactions, and we will talk about that. When you have partition, you have a liquid phase stationed on an inert surface, or immobilized on an inert surface, and your solute partitioned between this liquid and the mobile phase liquid. So it goes in and out based on its solubility. Ion exchange chromatography, we call it ion exchange. The term exchange means you are exchanging a charged molecule between a stationary phase and a mobile phase. So let's say you're positively charged, I'm negatively charged. Okay, so you're going to interact. The molecule is going to interact with the stationary phase, and then if the mobile phase carries a negative charge, you're going to go back and forth between the stationary phase and the mobile phase as a positively charged molecule. So that's why it's called exchange. The molecule or the ion is being exchanged, and that term confuses students a lot when we talk about cation exchange versus anion exchange. So keep that thought in mind. It's an exchange between the stationary phase that carries a charge and the mobile phase that also carries a charge. So the molecule is interacting. Let's say you have positive charges on your stationary phase. Your molecule would be negatively charged. It will be interacting with that positive charge on the stationary phase. In this case, it is an example of anion exchange because you have positive charge on the stationary phase, and anion is a molecule that carries a negative charge, and it is the molecule that is being exchanged. That's why we call it anion exchange chromatography. The opposite is true for cation exchange. All right, and then molecular exclusion chromatography, it's the same as size exclusion chromatography. So you can or gel permeation. All these terms mean the same thing. Size exclusion or molecular exclusion chromatography is based on separation by size. So this is the only chromatography where there is no chemical interactions between the stationary phase and your solute. So there is no interactions. They're actually just moving in and out based on their size and the pore size of your stationary phase. So your stationary phase has pores in it, and the smaller the molecule is, it will enter and go in and out and be delayed, go into the different pores and be delayed, whereas the large ones don't have access to all the pores because they're large. They will move faster down your column. So here, it is not an adsorption chromatography. It's not a partition chromatography. No interaction. This is kind of the single mode of separation that does not require chemical interaction for separation. It's purely on size. So ion exchange chromatography is one form of adsorption chromatography. Okay? So this falls under adsorption chromatography. It is your molecules are adsorbing by charge, by electrostatic interactions. Affinity chromatography is another form of adsorption chromatography, but it's a very specific interaction. It's like the interaction of a substrate with an enzyme, lock and key. It's very specific. Antigen with an antibody. It really is very specific to the molecule. So only the one molecule with the structure that binds to that particular ligand will bind, and anything else will not bind at all. So you are here selecting. You're not separating multiple. You are separating one particular compound from a mixture. You're not necessarily separating all the compounds in a mixture. You are selecting one. It's like when you're concentrating an enzyme or concentrating an antibody. You are really selecting one molecule. Okay. So let's talk more about each one of them. So adsorption chromatography, your stationary phase is solid, your mobile phase is liquid. So your adsorbent, which is the stationary phase, is a finely divided solid, so you have a small particle with a very small particle size. The smaller the particle size, the better is the resolution, and we'll talk more about that later. And it will permit differential interaction with components and allow them to separate. So you will have interactions. The interactions could be van der Waals forces, electrostatic, hydrogen bonding, or hydrophobic interactions. Any form of these interactions can occur in adsorptive chromatography. The one thing I want to point out, which is different from partition chromatography, adsorption coefficient is not constant. So in partition chromatography, partition coefficient is constant once you reach equilibrium, whereas in adsorption chromatography, it's not. And the reason is you have a limited number of sites where your compound can interact. So there's certain capacity, we call it. So you are limited. Let's say you have 10 sites. You're limited with the concentration of 10 molecules in your whatever volume you injected. If you have more, then you have poor separation because you end up with extra compounds that don't have room to interact on your column or stationary phase. They will wash out, and then you will get multiple peaks and you don't get pure separation. So what that means in adsorption chromatography, the amount you inject or put on the column is very critical. It has to be within the capacity of your stationary phase. That's where the concentration of your sample becomes very important. Because if your concentration is greater than the capacity of your stationary phase, then you will end up with poor separation. That is because your adsorption coefficient is not constant. So in adsorption chromatography, your stationary phase can be silica, slightly acidic, alumina, slightly basic, charcoal, nonpolar. The elution order often depends on relative polarity. So depending on how polar or nonpolar your solutes are. So if we're using pure silica or pure alumina, these are polar. So the least polar will elute first. The opposite is true for nonpolar charcoal. So something to note here is that your solute and solvent or mobile phase compete for active site on the stationary phase. And that's how, when you increase the strength of the mobile phase, you're increasing the competition, and that's why the solute leaves the column. We talked about that, or leave the stationary phase. And we talked quite a bit about that strength earlier. The stationary phase can be bonded silica, So if you take the silica, for example, and chemically bond it to C8 or C18, when I say C8 or C18, that means a hydrocarbon chain of 8 carbons or 18 carbons. The longer is the chain, the more hydrophobic it is. So when you use a column that is called C18 column, that is a stationary phase with hydrophobic stationary phase. That means it is going to be a reverse phase chromatography. Okay? C30, you'll find a C30. We use it for, Ali, we use C30 for carotenoids, right? Is it? But yeah, we do. It's okay. So the more hydrophobic your compounds are, you would go with a larger hydrocarbon chain. You want them to interact with your column so that they can get separated. Okay. Partition chromatography, I'm going to stop here because we're getting close to the end. So we'll continue. Okay, I'll tell you when we'll continue. I think we're going to continue this on Monday because this Friday I'm going to go introduce what you're going to do on the lab next week. So we're going to be doing something a little different than what we did in the past. We introduced a new lab. This lab is going to help you learn how to prepare reagents and buffers, which is a very important tool. So you will be doing that. Some of you did chemical reactions reversely, so you might have done some of that in chemical reactions, but you will be introduced to it here in this course. So I'll be going over that on Friday. I'll continue with chromatography on Monday.